Yeah, so let's get started for the section. Yeah, so in the last hour of our tutorial today, we'll be talking about this introduction to quantum machine learning, followed by a some sort of a small demo example of helping you building a simple binary classifier via our quantum machines, right? So just a gentle introduction by myself. My name is Kevin Gui. I'm currently a rising fifth-year PhD at the University of Chicago in the US. And now I'm doing this summer intern at the AWS Quantum SA team. Right. So before I started with the actual contents, for those of you who don't know machine learning that much, and then we actually know, I mean, like machine learning is actually a very important algorithms or sort of a set of algorithms, and nowadays has been developed for the past couple of years. I mean, sorry, has been developed in the past decades and have been starting flourishing in the past a decade or two, right? For instance, we can do some jobs like classification, which is basically to assign labels to some data values. We can do regression, that is the modeling relationship between variables. And we can also do clustering, and aka unsupervised learning, that is to help us to best organize data in groups. And lastly, we also have applications in deep learnings. For instance, how to build large neural nets to process data. Right. So here is a basic, like simple comparison between quantum machine learning versus our currently our classical machine learning. So for classical machine learning, which you just kind of see these two plots on the top. So for those of you who don't know, the sort of the idea of classical deep learning or classical neural network is to build this neural structures, right? So you have these neurons on the left that kind of pass as their input, and you have this end neuron on the right that kind of tells you what the predictor labels is. And also you have something in the middle, which is called the hidden layers, that is able to help you process all those data. And then on top of that, you have this sort of edges connecting the neurons. These are called the weights. And then basically you're training the weights sort of along different iterations to update them to make the best alignment with the corrected output, which is your training set. And then the way you kind of update these parameters of the weights is by doing something called gradient descent, right? So for instance, you have, sometimes it is in the perfect shaped curve. Sometimes it's not, and then it is either concave up or down. And then typically you do is this: you have some set of parameters values being passed in this neural network, and you pick a point and then say it's here. And then once you update the parameters, you may land in something that is a little bit lower, right? So you hope you keep this trend until you get to the bottom, which is the minimum value, right? Where in the bottom values here, you kind of reach the optimality that kind of optimizes your total neural network structure. So the idea of these variational quantum computing algorithms in general, or quantum machine learning algorithms, is try to mimic the structure of this classical counterparts, which is instead of building this classical neural network structure that connects the neurons, we instead build these set of quantum circuits. Right. So a quantum circuit consists of, as you may know from previous section, some sequence of quantum gates, and that kind of mimics the idea of these neurons and edges, and together with uh, some measurement or the expectation values in the end. And we pass this expectation value into the objective functions, right? And then we update the corresponding parameters, which is these parameters are instead of storing them in the weights, we actually store these parameters in the gate. So all these quantum gates are parameterized quantum gates. And then we do this gradient descent accordingly to hopefully get to some minimum. And then, so one caveat to notice is that this most type of these quantum machine learning or quantum deep learning algorithms are hybrid by default, because you are trying to do part by the QPU, which is the quantum processing machine, and you pass the parameters to optimize them in the CPU, which is the classical machine. So then innately, this is a hybrid quantum algorithms as defined. Okay, so one of the problems for this classical deep learning algorithm is that it's just intrinsically, very computationally intensive. So not only is it said you have to have a forward pass to pass all inputs and then give you a label, but then when you are trying to optimize all these parameters in the weights, you will do something called backpropagation, and then that is a very costly thing, which is that you have to compute all these partial derivatives and etc. and then to update it like weights by weights. And then so yeah. And then so hopefully we can try to come up with some potential speed up with the quantum circuits by saying we can have some this exponentially sort of compacted encoding space that can hope to find looking for some speed ups over the classical counterparts. And then again, up to now, and so people haven't I would say people have successfully demonstrated a lot of these interesting speedups, and then for processing quantum data. However, for the jobs where you are trying to process classical data onto a quantum machine is still hard, right? That is actually due to these the fact that we humans live in a classical world. I mean, most likely, and then all the data we gather are classical. So we need to find a proper way to encode these sort of feature values into the quantum machines to process. And then that process is sometimes not very easy, and then still a very active areas of research. So following that, let's first describe the general quantum machine learning architectures for those of you who haven't seen it before, right? So as I mentioned, the first most or the most one of the most important step for us to do is to encode our features in a quantum states. If your learning objectives is a quantum system, I mean, sometimes this can be a very natural process, right? There has been a lot of papers already discussing, for instance, quantum sensing, right? So we have some machines that learns and try to sense from some environment, and we're trying to learn these sense result from that, right? And then that is in general a easier job. However, given the fact that we are in a classical world, if we wanted to encode classical features in a quantum state, that is a harder job. Right, so this is the first step. And the second step is to design a parameterized quantum circuits representing the quantum neural network. So similar to the classical counterparts, and then these sort of neural network structures are in general very flexible. You can sort of design whatever the things you wanted. It's just a matter of is it good or not, or is it worse or better, right? And then lastly, you want to specify how to measure labels and then train a quantum neural network because in the end, all these encoded data are quantum data or quantum information, right? We need to find a way to extract these quantum informations to help us optimize them on the classical CPU, right? All right, so with this, let's first give some examples of how to measure and how to actually map your feature state to a quantum state. Okay, so the first idea is this sort of very simple idea called basic encoding, basis encoding. So for instance, let's assume that we have convert our classical features or any kind of features into this sort of a binary form, right? So binary form is where you only store the values in the zeros and ones, right? So for instance, if I have my first state is 0, 0, 1, 0, 1, 1 as a feature vector, then my corresponding quantum state will be exactly the same. But now I put them into the quantum state, which is the 0, 0, 1, 0, 0, 0, sorry, 0, 0, 1, 0, 1, 1 basis state of a quantum state. And then correspondingly, you have some other states that's mapped exactly in this form. So one of the problems for this type of encoding is that a lot of qubit space is not used if these features are sparsely distributed, right? Say I need 7 qubits to encode only 3 feature values, right? So that is not ideal if things are very sparsely being distributed. So here is like a little more advanced topics to sort of mitigate that issue. And then again, this it is only for those of you who have deeply interest in the math and everything around. And then so and if you haven't got the background yet, so yeah, feel free to just like take a little bit break out of it. So so sort of the extraction idea is this: given a classical feature vector of this x that has this each of the elements starting from x1, x2 until xn, right? So we have a total size of n elements of this x vector array, and then we want to find some better ways to encode these feature vectors. And then the first the first idea is to use this thing called the angle encoding, right? And then that is something which we can say that instead of encoding everything in a base, instead of turning all these values x1 and x2 into the binary states, now we actually encode all these values in amplitude of each qubits, right? Say This is exactly how we can process them as the cosine pi xi plus the sine pi xi in one particular qubit, right? And then you can sort of scaling them up by encoding them into many n qubits as you want it. And then more advancedly, there's another one called the dense angle encoding. Not only you can encode the amplitude as your feature vector elements, but also you can also encode the additional ones on the phase, right? Which is the some other interesting property of quantum mechanics. And again, you can tensor product this with only n over 2 qubits. So in this case, the dense angle encoding is able to give you a 50% saving over the original angle encoding. So the overall sort of complexity of this is that you can encode n number of features with all of n number of qubits, or in this case, n over 2 number of qubits, right? So that's for the angle encoding. And then here is a even more compact way you can do, which is called amplitude encoding. So given that you have this, again, the same x vector as a feature vector, right? You can actually encode each of these feature values in all of these in all the coefficients of these computation states. For instance, can have this I state spans the entire log n qubit space, starting from 0, 0, 0, 0, 0, 0, 0, 0, 1 until 1, 1, 1, 1, right? Because in total you have 2 to the power of n small n number of qubits, right? So then in the end, this will be a log of big N. I remember n is this big N is a number of the is the size of the feature vector, right? So it's a very interesting property that you can actually encode n big N number of features with only O of log n number of qubits. So that is a exponential amount of saving you can have, right? And then that is a very fascinating property that can only done by the quantum computer instead of the classical counterparts. However, I want to point out that to prepare this particular quantum state based on this classical feature vector is actually much harder than the angle encoding or the basis encoding, right? And then in fact, it will require a lot of quantum gates. And then I mean, to smartly sort of compute this quantum state is still active areas of research for now. Okay, so given that, let's start with the actual example where we can use this the simple basis encoding to actually try to solve a problem, right? And then here again, let's bring us back to this binary feature map, which is in this problem formulations. Let's say I'm interested in the parities of each of these binary features. So given these binary features, I want to count how many ones and zeros I have, right? So a parity is something like this. If I have a odd number of ones, then my parity is 1. And vice versa, if I have an even number of ones, for instance, like the second one, I have a value of 0, right? So the first binary feature have total of 3 ones, right? So 3 is an odd number, so I have a parity of 1. And then a second feature vector, I have a total of 2 ones, right? So then in total, 2 is an even number, and then correspondingly, I have a parity label of 1. I'm sorry, I have a parity label of zeros, right? And then the problem I want to solve is that I want to design and train a quantum neural network to reproduce the labels from the training set, right? So the idea is that given like some sort of a sparsely distributed training set, and then we can hopefully try to predict all the other binary features into its correct parity labels. Right. So this is upward encoding, and here is the second part, which is an example of the quantum neural network. And then so again, I mean, the actual design of this quantum network is very flexible. So this is only a one example of a quantum neural network. And then like in fact, like feel free to, I mean, like you're free to design any kind of structure you wanted. And then after this section, I mean, like so that will be another challenge, sort of a challenging problems that maybe you can do afterwards. Right. So, and the idea kind of goes like this. So after we first encode our feature vectors into the feature qubits, for instance, starting from x1, x2 onto xn, and then we add another one called label qubits. So the label qubit is able to tell me after the training that by only looking at this label qubits, I'm able to tell what the parity of the total feature vector is. So after this, we add the first layer of this RY gate. So RY gate is a single qubit parameterized gate that is parameterized by this data value. So these data values is going to be passed in the optimizer after you finish the whole quantum circuit and pass into the CPU to help you optimize this through gradient descent, for instance. And after the first layer of this RY, you have the second layer is called the entangling gate. And then, so for those of you who is familiar, that is something called the XX gate. And then this is a native gate in the ion trap device, or for instance, IonQ has this natively implemented. And again, this XX gate are also parameterized. So they have some parameters sort of can tell you what this gate exactly giving you. Right, so you can think of this as a little bit of this sort of a sine or pseudo convolutional structure, right? Where we're trying to convolve all these other features onto these labeled qubits. And then so by doing this entangling gate, controlling on the feature qubits and targeting on the labeling qubits. And then and here, and after the design of the quantum neural network, and the last part we need to do is to define the loss function. And then, so since our label qubits is measured in the commutation basis, right, we can easily define the loss function to compare the its true single label value y to the measurement value z. And then for the purpose of this, of this demonstration, let's design this to be something called log loss function, or if you someone recall, this is also called the cross entropy loss function. And then that is something that looks like this, that compares the difference between the true label value to the measured value, and we extract it from the label qubit. Right. So lastly, let's try to pull up everything together. So we have firstly all these data qubits encoding all my features. I have my label qubits that is ready to tell me what the true label is. And then we have some first layer of this RY single qubit rotation gate, and then followed by a sequence of the entangling XX gate. And that is also parameterized. And lastly, we take the Z-basis measurement, and then we tell this Z-basis measurement, we communicate this message to the classical computer, right? So the classical computer will compute the loss function for me, and then accordingly use some particular optimizer to update the parameters, and then back to the original part of the circuit, and then input this updated parameters inside my theta values, and theta 1, theta 2, theta 3, and then also the updated parameters for this XX gate. And then we go through iterations by iterations, so hopefully in the end, my classical computer log loss functions will be minimized such that it reflects the best sort of prediction of my label qubit. All right, so that will end my introduction to the neural network, and then we should be ready to go to the hands-on session where it actually shows you a particular coding implementation of the things I just mentioned. Yeah, so please go ahead and download
Can you
the
hear me,
Jupyter.
Kevin?
Yep.
Oh, okay. Sorry. We have a question from the audience. One question is this case different is this case y different to the y that is part of the dimensions of the qubit, label versus dimension?
Wait. Sorry. Can you repeat that question?
Yeah, it's not very well formulated, I'm afraid.
Mhm.
In this case, y is different to the y that is part of the dimensions of the qubit. Is that
So
correct?
so so are you talking about the loss function, the y values, or
Yes.
okay? So yeah. So you're asking why this label qubit has some different dimensionality than the feature qubits, right?
Yeah, I think that's
Yeah.
the
So why
question.
there's only one label qubit, but then
Sorry,
like there
yeah,
are
it was
many feature
perfectly
qubits.
formulated. It's just that I didn't read it correctly. That's the question.
Okay, got it. So, in the end, this is only one way you can design this quantum neural network, right? But so in fact, you can actually try to match the dimensionality of the feature qubit with your label, with the whatever the labels you are trying to extract. It just in this simple cases, we're trying to put everything we have from the future qubit. We're trying to extract information from those, and then sort of pipe them into label qubits, so that is easier for us to tell easier for us to define because since now I only have one label qubit to worry about, right? So it is easier for us to define the log loss function based on the single label qubits. So of course, also in many other proposed algorithms, you have some you want to sort of extract all these feature qubits values, or then after some some sequence of quantum gates in the end, right? So and then you want to process some sort of a equal dimensionality of the labeling qubits afterwards, right? So that is also totally possible. It just in next examples, we'll try to simplify these problems for easier demonstration. Yeah, it's a very good
Excellent.
question.
I think it does. At least I understood. We have another question. Why is Rx for the label qubit and Ry for the features?
Okay, so I mean, like, in principle, you can do anything on the label qubit. It's just like, we put the Rx on this thing on the label qubits because, it works better, right? I mean, either it kind of help us reach the local minimum in a faster pace, or, it kind of help us, sort of swap between the zero and ones, right? So notice that in the log loss function, we are only interested in if the labeling qubits is 0 and 1, right? So doing something in the Rx that kind of exactly swapping between the 0 and 1s, right? So, the RY also kind of is rotating me in some different angles, and then sometimes it might complicate things. Yeah,
Thank you.
so of course you can also do like some RYs. That is totally possible, but yeah, it makes things a little bit simple in here.
I was about to answer another question, but I will let you take it as well since you're in a role. Why do you need classical computer to calculate the loss function? If this is a trial step, why can't this be done in the quantum piece?
Yeah, exactly. Yeah, so that is also a very good question. And one of the reasons we want to use a hybrid algorithms in this case is that these type of particular type of machine learning algorithms, quantum machine learning algorithms, are designed for NISQ purposes. So NISQ stands for near term, or what's called a noise intermediate scale quantum computer, right? So given the fact that some quantum machines are a little bit noisy, and then we cannot run the circuit for too long, and then we have to rely on the fact that we want our CPU to help us in the process, such as it may actually alleviate the sort of the burdens of an entire total QPU we have, right? So that is actually similar to one of the previous session you have for the quantum chemistry section, is that we wanted to use our CPU to help us optimize the variation parameters and from that QPU. So of course, in the what's called the longer term structures, you can maybe design some other smarter methods. So you can use your QPU to optimize your parameters, but that is still up in the air. And then people haven't are I mean are still doing active research on the area, saying how do you design efficiently QPU optimizer to optimize the parameters, and then that will be something hopefully in the long term that will come out.
Thank you. I think there was another question about suggesting QNN papers, but we can take care of that as part of the
Mhm.
materials that we are going to share after the
Sure.
session. We will throw a few papers there. Thank you for the question.
Mhm.
Go ahead, Kevin.
Yeah, so for that, let's actually start of showing up some other interesting examples we have just mentioned into a Jupyter notebook, right? So I believe Juan has, or if not, he will share you with the link that has download like the download file for this, right? Yes.
Yeah, I shared it before. It's the first file, the last file that we haven't used today. And this time you can place this file in any location you want because there's no dependencies with other folders. So if you want to put it in the root folder, feel free to do so. It's fine.
Mm-hmm. Yeah,
Thank you,
let
Kevin.
me share my screen again. All right, cool. So
Try to make it bigger so we can see better for those with a smaller screen like me.
yeah, let's do this. Yep.
Awesome. That's much better. Thank you.
All right. So in the first section of this notebook is a little bit like sort of backgrounds and math and the exact mathematical formulations, right? And then feel free to go over like afterwards, because these are the actual the sort of formal math languages that kind of defines the problem. But in the interest of time, let's try to dive directly into the code that we can show you, and then feel free to work through all this math and afterwards, right? So again, essentially, to define a successful quantum neural network takes three parts. And then the first part is again to actually design a way to map your binary feature states onto the quantum states of the qubits. So let's take a look at the code. And then, so remember, we wanted to pass some feature strings as I mean, sorry, for some as a string values, right? So for instance, I define my feature to be some strings that sort of consist of the zeros and ones, right? And then I define this method is called bitstring to circuit, and then that is parameterized by the actual bit strings you want to pass into, for instance, this feature. And then now let's first initialize a quantum circuit objects, and then here is this kind of for loop that actually does like this. So imagine it kind of the index kind of iterate through all the ranges of the bit string, right? Say for each element of the string, if this particular indexed character is a 1, then I do a circuit.x. So this is essentially doing x gate on this particular index qubits. And then what it does is that it kind of since everything is originally initialized in the 0 state, so this x gate is trying to turn your 0 state into the 1 state, and then correspondingly it turns into the 1 state into a 0 state by the reversible rule. But then like in this case we don't actually need it, right? So anything that is a 0 state, if the corresponding bit string value is a 1, then I turn the corresponding qubit value into the 1 state. So yeah, so let's say in the first example, I give this 0, 0, 1, 1, 1, 0, 1 state, and then let's execute this and see what it happens. Right? See, um, since the Python is zero indexing, right? So we have our first one's located in my third position. That will correspond to my Q2. And then we'll add an X gate in here. And then also correspondingly at my fourth location, fifth location, and seventh location of the ones, right? So I will do Q2, Q3, Q4, and Q6 with all the X gates added on top. Right. So you can for your if you want to play with it, you can try some different versions. Like so, let's say if I wanted to do something else, right? I want to do 1, 1, 0, 1, 0, and for this case, now I can see that my Q0, which is my first qubit, and then Q1 and Q3 are being added to an X gate correspondingly, right? Yeah. So let's stop here to see if there are any questions so far. Okay, so I think why I'm trying to talk something, or because I couldn't really see the question list. Juan, I think you are muted.
Oh, apologies. I was saying that the question was hybrid algorithms will consume more resources while multiple conversions between circuits and weights. I'm not sure it's very well formulated, but I guess the question is how the efficiency it is when you are executing a hybrid algorithm. If it's better or worse than running an all in classical computing machines.
Yeah, so that is also another excellent question. So I would say for now, people don't actually know that yet. And then so far, nobody have ever proved any real quantum advantage of trying to learning classical data on a quantum machine. So that is still an open question of whether or not we will actually need this quantum machine learning algorithms or not, right? Because the classical machine learning algorithms are already powerful enough.
Got you. What are QRAMs? Is there any plans to have QRAMs in Braket? I don't know what QRAMs are. I'm gonna hold that question to give you a proper answer, Deeks. Thank you very much. I'm learning something from you today.
Cool.
One more question and we can continue. What happens to your initial? Oh no, that was my question. I launched that as a launch to the audience. Don't worry about me. You can continue, Kevin.
Awesome. All right. Sweet. So hopefully that is understandable enough. And then now let's try to buckle up. And then here it comes the more complicated part. Okay, so the next step after the feature encoding, and then the step is now to define the actual quantum circuit, and that kind of shows you this quantum neural network structure. Okay, so the first thing again is to import a bunch of these libraries to help you make things work. And then the first step we want to do is to set our bracket breakends. For instance, in this case, I call this device equals to a local simulator, and then in the actual, in free time, feel free to change it to SV1 or any physical machine. But for the purpose of this demonstration, let's keep it as the local simulator because it will just and I mean, we'll probably run faster than the other parts for now. Right. So here is the sort of meat of this quantum neural network structure. So I define this circuit called QNN, and then that is again parameterized by my bit stream. So I want to pass some feature vectors, and then I first want to encode them onto the machines, right? And then I also parameterize it by some values of the parameter. So this parameter is first being passed into this QNN and to actually construct your quantum circuits. And again, in the actual optimizers, we're also trying to pass these parameters in the classical CPU that help us optimize this to hopefully reach some minimization according to my single QNN in here. Right. So first we wanted to collect the number of qubits by calling this length and plus one, right? So we want this additional qubits that is allocated. Remember, like we have some number of feature my working qubits to encode the features, and then I will have one additional qubits to encode my labels, right? And then now let me again call the constructor to initialize the quantum circuits. And then we first do this thing is called the qn.rx. And so
Seems that we lost Kevin. All right, we are back.
hello.
Hello, we lost you for 5 seconds.
Oh, sorry. So let me try to repeat that what I just said. So the first step is want to do this qn.rx. So this is to add the rx gate, Primaris rx gate on the labeling qubit, which is the labeling qubits in here. Right. Okay. And then next, let's try to go through this for loops together. Right. So for loops first iterate through all the ranges of the qubit numbers on the working qubits, or sorry, on the data labeling qubits. And then first is kind of extract the angles by the parameters. Right. So this if statement is again to help you to encode your quantum features by calling this x gate if the particular bit stream index is one. Next, let's add the quantum Rx gate for here, which is the first layer. You have this in the green bar, other than the sorry, the RY gate green bar in here. Right. And lastly, we do this another sequence of the XX gate, which is you can call them like either one time or twice. I mean either one that's fine. So we can do QN and .rx and again QN .xx. But then like Braket has this ability to sort of doing simultaneous gating sequence, and then you can call this XX gate after the RY operations, right? So again, this XX gate is parameterized by these angle parameters. Um, that kind of shows all these purple bars in here. Okay, so lastly, after this gating sequence, we want to add a z observable to the label qubit so that I can again measure the output. I kind of for all the scramblings I've been doing in the first part, I mean, of the quantum neural circuit, and then I call the expectation values to extract the output. And lastly, I return these quantum circuits I defined in here. All right, so next, okay, so let's first stop here to see if anyone has any questions for the quantum neural network part.
Yeah, we have a question from Rafael. He wants to know, where did you define the angles?
Okay, so the angles is again passed as a part of the parameters, right? So for instance, like in the first Rx gate, right? So I want to pass the first parameters in half, and then so Rx gate is done like this. So the Rx gate itself has two parameters inside this methods. The first method is to define what is the location of the qubits you want this Rx gate to land, right? So in this case, I want this location to land on the last qubit because that is where my label qubit is positioned at, right? And then next, I pass the parameters of the angles as my second parameter, which is the first index of my parameter and my parameter array. So similarly, you can pass your angles in the RY gate, right? So RY gate is again, and the first parameters is where you want your qubits I mean, you want this RY gate to land on which qubit, and then you want to pass the angles as the parameters on the second parameters of this RY methods, and then the same as the XX gate. So the XX gate has the first parameters defining your controlling and target, sorry, the controlling bits, and then the second parameters tell you the actual target bit locations. And lastly, the angles is your parameters angles you want to have in here.
Great. A follow-up question on that from Kai-Chun is angles should be allowed to be generated in random, right?
Right. Yeah. So in the actual classical optimizer, you can try to start with a arbitrary set of the parameters, or you can design some smart way to start in some midpoint of it. I mean, depending on your particular algorithms in the end.
And one more question from Jorge. How big can this be, or have you tested how big you can be?
So in this examples, we have a total of 11 qubits as my label. So, in theory, this can go up to like sort of 20 or 30 if you run on the S1 simulator. And then, but like, be warned that, all times if you go like say 100 something, you'll maybe blow up because that is sort of what is called the limitation of this classical simulation of quantum algorithms. Because if my classical machines is powerful enough to simulate my quantum system, then what is then my quantum advantage, right? So in the long-term cases, and if you want to run like say like a sort of 1,000 or a million size of the qubits, and it's better be done on the real quantum hardware because that is where the true quantum advantage will show. An example, we're only gonna give you like a very small example. Yeah, that's a very good question.
Thank you, Kevin. No more questions for the moment. You can continue.
Awesome. All right. So the next part is where we can try to define the loss function, right? So to actually define this loss function, I defined and sort of I iterated before. We first needed to build a function that actually tells me what the parity is, right? That is gonna be the sort of either the true label I want to pass in a training set. So again, we just simply count the modulo of 2 on the number as 1 we have in here by calling this count with modulo of 2, right? So if there's an even number of ones, then I get 0. If there's an odd number of ones, I get a 1 in here. Oh, sweet. And then with this parity function defined, and here is the actual cost function. So again, the cost function is parameterized by your training set, which is the actual labels you want to pass into, and then there's also by the parameters you have, and then the device, right? So because I want to run first, okay. So here let's begin with the for loop, right? So I mean, in this simple example, and it's a simple aggregation of all the training set, right? So we first want to iterate through all these training sets. So we want to make sure that, so for instance, if I have some array of the bit string, for instance, 0, 1, and 1, 0, 1, 0, 1, 0, 1 up to 0, 0, I want to make sure I iterate through all the training sets to go through, my feed forward neural network structure, right? So I want to, get an aggregation or a collection of the loss function you have. So that is why I wanted to iterate through the entire range of this training set. Okay, so for each individual points and data points in the training set, I first call this queue and tasks, right? I call the device, and then which is I previously defined as the local simulator in here, right? And then I call it device.run, which is to actually execute your job on either on a device you have. And then we call the parameters, which is this queue and circuit I defined before. And then and lastly, I do short equals 0. So notice that short equals 0 is where you have things actually output to the exact sort of the and wave function vector. So in the real physical machines, typically you have to define short to be some positive integer value, for instance, 100 or thousands, to actually extract the actual physical measurement output. But then, like in this case, for simple demonstration, let's just leave the shot equals 0 to give us the full wave function state vector. And then you have this thing called the result, and then I can call the result of the tasks. And this part, the if and else statement is where you are replicating exactly the log loss or the cross entropy loss you actually defining here. Right. That's the last if statement it's gonna give you in here. So and then you print out the result of this and then return the cost, right? So that will be the cost function where we pass in the optimizer we have, which I'm going to show you in the next step. Yeah. So any questions so far for this part?
I have a question, but I'm going to table it because we are close to the end, and I want to make sure that everyone has an opportunity to run this and play with it a little bit. So you can
Got it.
continue,
Sure.
Kevin.
Yeah, I'll come back to this once we start the optimizer, right? So it's gonna take a couple minutes. Right. So lastly, let's here is our final step. we want to pass whatever we define, right? The encoding part, the quantum neural network part, and then the loss part into this, right? So as we mentioned before, we first want to initialize some assignment of the parameter array as in here, right? So these are we call this np.random function, right? So this is going to give you some arbitrary values of the parameters in here. And then we wanted to make this random angles between minus pi and pi. And this is exactly where the actual quantum bits are ranging from and with angles. Right. So now a loss function is where you can start with the games, which is this minimize function from scipy. You can define your lambda function here as your cost as a cost, and then you have some set of parameters in here, and then lastly you have this corresponding optimizer methods. You can do this BFGS, or you can do some other ones like, for instance, atoms or another mean, and etc. And then lastly, we want to display the options in here. So yeah, let's start with this. Okay, so first I have to execute all the above cells to make this work. So let's first do Cn, Qn, and then the parity and the cost. And lastly, I start this. Okay. Damn. I think I probably lost a VPN for this. But yeah, for your case, feel free to start, and let me just reconnect my VPN so that I'll have access to this thing. Hello?
Yeah, we hear you.
Yeah, I was just trying to reconnect to my VPN so that I can get back again to my Isengard console. Sorry
No
about that.
problem. No problem. Take your time. We still have 7 minutes, so people still have
Yeah, we should be good.
opportunity to.
Let's go back to the notebook we have in here. All right. So you can scoop my screen, right?
Yes, we can.
Sweet. Let's try to execute everything again. Right. We have this. We have our cost function in here. Yeah. So here we go. And then you can see this optimizer is actually started to, go through the iterations and try to minimize the loss function, right? So you can see that the loss function start with 11.97, slowly goes down to 10 to 9, and then to 8, and etc. Right? So this process will probably take you, a couple of minutes depending on how your local simulator behaves, right? Right. So in the while this is working on, let us try to go back to the previous question. One, can you remind me what's the previous question again? So that
Sure. Yeah. Ramadas was struggling to see how this was an ML problem when we are defining the function. Um, he's asking how the level is calculated as sum of one or of mod two. In ML, in traditional ML, we will expect the weights to be learned without defining the function. That was his question.
sorry, can you repeat that? I couldn't actually.
It's a long question. How is this an ML problem? When we are defining the function, how the level is calculated as the sum or one mod two. Whereas in ML, we will expect the weights to be learned without defining the function.
Okay, got it. So so asking sort of differences between the quantum circuit part in the QNN, in the QNN versus the classical neural network,
I
right? The
think that is
Wizard
the
part, right?
question, yeah.
So yeah, so here is that's another good question. So I would say the quantum neural network structure is not the exact replicate of the classical neural network. So in the end, there are some sort of subtle differences. So the parameters I have, again, in this part is your sort of your a not a very good analog of the classical weightings learned from this, right? So it is instead you can think of these quantum circuits as kind of your hidden layers or whatever things you have. So like since there are some subtlety of saying there's a thing called quantum no cloning theorem. So you can not exactly do the exact backprop operations as the classical neural network. So that's why things are looks a little bit differently in here. Right? And then there are some other subtleties where sometimes it's hard to create some sort of a nonlinear activation functions in a quantum neural network. You have to go through some sort of a repeated process in here, which is not very easy. And then again, this is another interesting topics of how do you add the nonlinearities as your activations in here, right? So yeah. So short answer is that QN is not exactly the same as the classical CNN. Yeah. Right, so let's see how our optimizer goes. Okay, so it goes pretty far right now, up to zeros. All right, so we're almost there. Up to, okay, 0.006. Yeah, so hopefully we'll finish in a minute or two. Right, here we go. Kind of goes to very good values now. All right, so here the optimizer is telling me to terminate because we have successfully get to a very low net value of the loss function. And then yeah, so we can sort of see here is that the total number of iterations that go through this optimizer is a total number of 99 times. And then I evaluate 2,800 quantum functions in here, right? And then now I can call this res.x to actually output the what's called the optimized parameters values in here. And then I can copy and paste this thing into the other one I want to call in here so that I can be ready to pass in the validation function I have, right? So I execute this. Oh, sorry, let me import this thing again. mp.array. So it's not complete anymore. And then let's now work through the validation. Okay, it's not going to take a while. Oh, here, right? So and this validation functions in the end is trying to first go through all the possible bit string, and because that is essentially very different from the training set, right? In the training set, we will only have a total of like say around 10 training examples, so that is definitely not covering the entire set of values. And then we want to examine for those bit strings that is not covering a training set, is it going to actually also give us the correct output, right? So that is the actual powerful things that machine learning can do, is to predict the things we don't actually know before, and basis on some other known information. Right. So so here you can sort of see it kind of tells us all these most of these are not in the what was not in the training set before, and then we have these sort of first feature as all the zero, and then it can actually tells me there's no ones, right? So there's a total zero parity in here, and then the first feature is in here, and then that is actually in the training set, and then it has a parity of 1, right? And then you can favorite scroll scroll down for all these feature vectors not in the training set. You can see that it has successfully predict. I mean, say here you have a total of 5 ones, then I have a parity of 1, and then in this case, I have 4 ones in total, and then correspondingly I have a total parity of 0 in here. Right. So yeah, so that's pretty good. We kind of knows that my machine learning algorithm is actually doing all the things I wanted. So yeah, and hopefully we should be in good shape. And then you can I mean, another sort of a challenging problem for you to do in the future is that you can try to toggle these training sets such that let's try to use the least number of the training examples to give us the best sort of validation output in here, right? So that is something you can feel free to try in a later time. Yeah, so that will end for this notebook demonstration. Yeah, feel free to ask me any last minute questions so far.